and welcome back. Today we're going to begin discussing the topic of ANOVA. Now, ANOVA is an extension of a two-sample t-test. Recall in a two-sample t-test, we had a null hypothesis that said mu1 equals mu2, and an alternative hypothesis, mu1 was not equal to mu2. We had two populations of interest, and we wanted to determine if these population means are different. However, with ANOVA, perhaps we have K populations, and we would like to know if any of the means are different. Now, one naive approach that we could take is to compute all pairwise comparisons. That means we would do all two-sample t-tests for all pairs. This would mean we would wind up doing as many t-tests as we needed. And so our null hypothesis would be that mu1 equal mu2 equal mu3 equal mu4 equal all the way up to mu k. And our alternative hypothesis would suggest that at least two of these mu's are different. Well, suppose we have three populations. So we're going to compare mu1 equals mu2, mu1 equal to mu3, and mu2 equal to mu3. This gives us three comparisons. If we extend our number of populations to 4, we see we're comparing mu1 to mu2, mu1 to mu3, mu1 to mu4, mu2 to mu3, mu2 to mu4, and mu3 to mu4. That means we have 6 comparisons. But what happens as we get larger and larger populations? Suppose k equals 7. Well, now we have to compare 21 different pairs. That's a lot of comparisons. So, in general, if we decided to do the naive approach and do all pairwise comparisons, we would have k times k minus 1 divided by 2 comparisons. And within each of these comparisons, there's a type 1 error associated with its particular t-test. Now, if we suppose that alpha is 0.05, then 1 out of 20 of these are likely to be wrong. However, but by doing all pairwise comparisons, our type 1 error rate for all our pairwise comparisons is now transformed into an experiment-wise error rate. And so alpha sub e, our experiment-wise error rate, is going to equal 1 minus the quantity of 1 minus the comparison error rates raised to the k, where alpha sub e is our error rate for the experiment, and alpha sub c is our error rate for each comparison. Now, how does this impact our error rate? Well, if we want to control the error rate for our experiment and still be able to test the hypothesis, let us suppose for a moment that our comparison-wise error rate is 0.05. For 3 populations, our experiment-wise error rate is then 1 minus the quantity of 1 minus 0.05 raised to the third. That gives us an experiment-wise error rate of 0.1426. When we increase our populations to 4, we now get an experiment-wise error rate of 0.1855. And if we increase to 7, we now have an experiment-wise error rate of 0.3017. Our alpha sub e, our experiment-wise error rate, is then the probability we make a type 1 error on at least one comparison. Remember, we said there are k times k minus 1 divided by 2 possible comparisons. So at 3 treatments, we have 3 comparisons. For 4 treatments, we have 6 comparisons. And for 7 treatments, we have 21 comparisons. But let us suppose for a moment that there are 12 populations. And so k is going to equal 12. Well, then how many comparisons must we make? 66 comparisons. Now, depending upon our alpha that we've chosen, let's see what type of experiment-wise error we might get. So let us assume for a moment that alpha sub c, our comparison-wise error rate, is set to be 0.01. So our experiment-wise error rate for this, let's say our 12 population, is 0.1136. This means that a little over 10% of the time, we're going to make an error in our experiment. However, let's set our comparison-wise error rate to 0.02 and see what happens. Well, now we get an experiment-wise error rate of 0.2152833. So a little over 21% of the time, we're going to make an error in our experiment. If we then increase our comparison-wise error rate to 0.05, our experiment-wise error rate goes up to 0.4596399. So over 45% of the time, we're going to make an error. If we then increase our alpha to 0.10, our comparison-wise error rate to 0.10, what happens? Well, with these 12 populations, we get an experiment-wise error rate of 0.7175705. This means that over 70% of the time, we can expect to make an error somewhere in our experiment. This is not good. And so we need to find some type of a mechanism that we can use so that we can try to control this experiment-wise error rate and still do our tests. That concludes this particular video. In our next video, we'll start talking about how an ANOVA can be run and begin with completely randomized designs. See you then.